Good afternoon, class. We're looking at college algebra practice test number 3, module 3, chapters 5 and 6. And here's chapter 6, exponential and logarithmic functions. We want to find the formula for an exponential function that passes through the pair 0, 2000 and 2, 20, where f of x is given as a b to the power of x. So basically, we are going to replace the x with the first coordinate, in this case 0, and f of x or y with the second coordinate 2000. That's one pair. We do the same thing with the second pair. We replace the x with 2 and f of x or y with 20. The first one, b to the power of 0 is 1. And so a becomes 2000. So we are going to replace the a with 2000. When we work with the second one, we replace the x with 2 and f of x or y with the second coordinate, namely 20. We can divide both sides by 2000. Gives us 1 over 100. B has two answers, 1 over 10 and negative 1 over 10, but we only keep the positive because of the restriction for exponential functions where the base must be positive, and therefore f of x is 2000 times 1 over 10 to the power of x. Here's the next question. Les deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it is compounded monthly? So here's the formula for compounding. I hope you remember the basic formula is I equals PRT. Simple interest. This is the compounded version. And so let's replace what is given to us, P, the principal with $10,250, or the rate is 0.044%. And T is 10. Now, I'm not going to replace the N yet. In general, I'm going to keep it as N. For this part, monthly, N is the number of compounding per year. So if it's annually, it's 1. If it's monthly, it's 12. So replace the N with 12. And all you have to now plug it into a calculator, of course. Just 12 times 10 is 120. Add these two numbers, raise it to the power of 120 times $10,250. And it gives you $15,000, $281.03. By the way, because we are dealing with money, we normally go with 2 decimals. Same question. Instead of monthly, we're going to do weekly. So that's why I'm going to go to that formula. See, the T was 10. And the only thing I'm going to change, N over here was 12. Over here is 52 weeks. So 52. And again, put it into a calculator. Obviously, it becomes a little bit more than the previous one because it's compounded more often. If we do it continuously, we get to the formula A is PE to the power of RT, the exponential growth, and we replace the principal, the same principal, $10,250 rate with the same rate of 0.04, and T is 10. We let this, of course, the product is 4. We let the calculator give us the answer. As you can see, this is the highest value among all of those. With exponential growth, we also have something called doubling time, the amount of time it takes for the initial amount to double up. Now, it doesn't matter what the initial amount is. It's really independent of that because On the left side, we are going to write this 2 times whatever this is, which is p, so we make it 2p. And with that being the case, p cancels out and 2 is e to the power of RT. I hope you realize the key is the rate. So how do we solve this? We take the natural log of the both sides. Why natural log? Because the base is e. So the left side becomes ln2, the right side becomes RT. And since we want to solve for t, it's ln2 divided by r. So what matters is the rate anytime you want it. And this works always. ln2 divided by r. In essence, we proved the doubling time has the formula ln2 divided by r. And we know r is 4%, so replace it with 0.04. And remember, ln2 is not missing. It's an exact answer. You put it into a calculator and you come up with the answer. And however many decimals they ask you, in this case, I put many decimals. So when you want to round it, you round it according to the given question. 17.32868, a little bit more than 17 years. We have been given a bunch of exponential functions. We want to use the graph to answer the following question. And all of them have this format of f of x equals ab to the power of x. Which graph has the largest value for b? Which graph has the smallest value for b? Before we answer this question, I want to remind you of a couple of things, everybody. Number one, if you recall, when we write an exponential function, y is a to the power of x, a is positive, it looks like that. So for example, we know this has a positive base, so on and so forth, okay, on the right side. When we look at the green one here, that's an exponential decay where the base is somewhere between 0 and 1. Another example, if you recall, we can write, for example, if this is 2 to the power of x, we can write 2 to the power of minus x, or this is the same as 1/2 the power of x. That's another way of writing it, okay? So I hope everybody is comfortable with that. What else do I want to add? If you look at this function, for example, look at the base. The base is 2. When it gets larger, it gets closer to the y-axis. If this number is larger than 1, if the base is larger than 1, and it's on the right side, it gets closer and closer to the y-axis when the base gets larger. Now, ab to the power of x, assuming a is larger than 1, in this case, of course, it's 3, but in general, abx, what happens is that the coordinates here, what would be the coordinates for the y-intercept? 0, 1, 0, 1, 0, 1. All of them are 0, 1. For this one, becomes 0, a, in general, a, okay, 0, this case, whatever this number is, which happened to be 3, but 0a. So I wanted to remind you of that. So in this case, which one has the largest value of the base? The one closest to the y-axis on the right side, and that's the D graph. This is closest to the y-axis, graph of D. Which one has the smallest one? The one which is the furthest. So closest to the y-axis on the left side has the smallest value, because we're going to go with this one, okay? For example, 1/2 x. So that's what we mean. We're not going to go with the negative exponential, but rather look at this base, okay? In essence, 0.5 corresponds to 2, okay? In essence. So for that, we have the green one, graph of C. That's closest to the y on the other side. Now, which one has the largest a, which one has the smallest a? And so if you replace in this formula or in that formula, if you replace the x with 0, you notice the y-intercept takes place at 0a. So the largest a, the largest y-intercept would be, look at this. This is the y-intercept, this one, this one. This one has the largest y-intercept. So it's the green one again, graph of C. And which one has the smallest one? Look at this. This is a y-intercept. This is a y-intercept. This is the smallest of all. And that would be the graph of the f function. We want to use transformation for the basic function y or f of x equals 2 to the power of x and arrive at these two. So, and of course, we want to discuss the asymptotes, domain, range, so on and so forth. So we start with the basic function looking like that. Remember, when the base is larger than 1, generally speaking, looks like that, and it has a y-intercept of 0, 1. Since we want x to be changed to minus x, then we are going to reflect it with respect to the y-axis. So this flips over with respect to the y-axis. And it looks like that with the same y-intercept. And now the graph has the equation y equals 2 to the power of minus x. We have the same horizontal asymptote, which is the x-axis of y equal to 0. We have the same domain as this one, all real numbers. We have the same range, 0 to infinity. So what has changed is that this is an exponential growth, this is an exponential decay. So that's part A. For part B, go back to this one and we shifted up by 1 unit. We're going to shift it up by 1 unit. So what happens is that this is the function of interest. This is the asymptote, which was the x-axis. Now it's the line y equals 1. This is the horizontal asymptote. And this had coordinates 0, 1. Now it has been shifted to 0, 2. So maybe I write that. So this has coordinates 0, 1. Has coordinates 0, 2. Horizontal asymptote y equals 1. And the domain hasn't changed, still all real numbers, but the range in this case was 0 to infinity. In those two cases, now it's gone up, so it's from 1 to infinity. So it has affected the range, obviously. Here's the function f of x equals 4 to the power of x. I'm going to write the function that results from the given. For example, in part A, we want to shift it 3 units up. So to take this 3 units up, we're going to add 3. We want to go 5 units left. So again, we are going back to original function, not this one. Okay, we are just working on the original function. So we want to go 5 units left. We're going to change the x to x plus 5. Going back to the original function, we want to reflect it about the x-axis. And so we put a negative sign in front of 4 to the power of x. And finally, we want to reflect it about the y-axis. Again, we are going back to original one. So that means we're going to change the x to minus x. I'm giving them just different names. G of x, h of x, k of x, I of x. Transformation. We are supposed to work on this. F of x equals to the power of x, and then end up with this one. And we want to write an equation for the graph shown. Well, we start with the original function f of x or y equals to the power of x. Whether it's to scale or not, it's not that important. So we are going to start with the reflection. Across the x-axis. So it looks like that. So this is y or f of x equals to the power of x. This one is minus 2 to the power of x, because we notice it looks like that. So this, and then we notice that it looks like that and it's been shifted up. If we were to graph this, there seems to be a horizontal asymptote here that has been shifted up by 1, 2, 3. So if we shift it up by 3 units, goes up like that, we draw the horizontal asymptote y equals 3. On this one, it looks like that. And the function is f of x equals the same thing plus 3. And that's the final answer. Minus 2 to the power of x plus 3. So these are some transformations. Now, I want to remind you of logarithmic properties, and to really understand this, remember the base must be positive and it can't be 1, just like the exponential. To understand it, let's look at this and the arrow that I put in. If we can follow this arrow, the base b to the power of y equals x. Look at this arrow, b to the power of y equals x. If we can make this transition, every property that we have discussed becomes a piece of cake. Log 1 is 0, log b is 1, and so on and so forth. So for example, you can clearly see b to the power of 0 is 1, b to the power of 1 is b to the power of x is x, so on and so forth. This is the product rule, this is the quotient rule, this is the power rule. These two rules refer to the fact that exponential functions and logarithmic functions are inverse functions. And when the base is e, we use ln, and we should be able to make the transition, I hope. And by the way, these two give us the same properties, right? And ln1 is 0, ln e is 1. Remember, when this means when the base and the argument are the same, the answer is 1. Since we write ln, the base is e. So it becomes very straightforward. In the case of a common log, when we write log no base, the base is 10. And again, log 1 is 0, log 10 is 1, because the base and the argument must be the same. And again, numbers 3 and 4 here and here and here, they are telling us that logarithmic functions, exponential functions are inverse of each other. For example, y equals ln x and y equals e to the power of x. Therefore, they are symmetric with respect to the line y equals x. Here's the change of base formula, because when we want to evaluate logs with different bases, we normally go to either common log or natural log. So log x base b, we use ln x over ln b or log x over log b. All right, we want to rewrite this, and all we have to remember is the basic formula. So 5 to the power of q is m. This one, when we have ln, that means the base is e to the power of z is v. When we have log and no base, the base is 10. 10 to the power of t is w. So maybe I write this in this format. So look at this error. So we have those answers. Now we want to go back, where we want to go from the exponential format to the logarithmic format. For example, this one, log y when the base is 3 is x. Since the base is e, we're going to go with ln of h is k. This is not 10, so log b when the base is 100 is a. We'll write the domain, vertical asymptote, and the end behavior of the function. And by the way, with the exponential function, we had horizontal asymptote, and now we have a vertical asymptote. So first and foremost, it's the same as y equals log x. It's been shifted to the right because it's x minus 7 by 7 units. So this is the original function, and now it's been shifted. So when this one has coordinates 1, 0. Now this has coordinates 8, 0. And the domain is 7 to infinity for this one. For this one is 0 to infinity. I hope you remember that. For this is 7 to infinity. The range is all real numbers and it's not changing. So we write this point has shifted to that point. Okay. And again, if you want, I can write next to it. This had coordinates 1, 0. The new one has coordinates 8, 0. And the vertical asymptote has the equation x equals 7. Domain is 7 to infinity. Range is minus infinity to infinity. I want to make sure everybody understands what happens here is that the domain for the basic log, this is y equals log x, this is from 0 to infinity, okay? Now it's been shifted to the right by 7, so 7 by 7 units, so 7 to infinity. So what is the end behavior? What happens as far as the end behavior is concerned? When x goes to 7, and by that we really should say 7 from the right, this goes down to negative infinity, and when it goes to infinity, f of x goes to infinity. I hope you can see that. So when we get closer and closer to 7 from the right side, it goes to negative infinity. On the right side, this keeps on going, okay, forever. All right, we want to work on this one, and we start obviously with ln x, y equals ln x, and we change it to ln of minus x when that happens. And so the transformation is a reflection across the y-axis. So this is y equals ln x, and this is y equals ln of minus x. Now to get to this one, I hope you see that it's minus, you can write it as so that's the point. This is a new point. And now if we write it in this fashion, That means we are shifting it to the right because it's negative, shifting it to the right by 2 units. And so this one moves to the right by 2 units, and this coordinate, which was negative 1, 0, it goes back to 1, 0. So let's put that point in there. Let's do the drawing, and that gives rise to the vertical asymptote of x equals 2. This is the intercept, okay, 1, 0, and I can write that. Maybe I write it here 1, 0, over here is negative 1, 0, and it's going back to 1, 0. Okay, so what happens is that the domain has changed. Now the vertical asymptote x equals 2, as I mentioned. And what happens to the domain is from negative infinity up to this number, that means 2, from minus infinity to 2. The range is still all real numbers. So as x gets closer and closer to 2, this time 2 from the left, it goes to negative infinity. And when x goes to negative infinity, it blows up to positive infinity. Again, that would be the end behavior. All right, we want to work on this function. Again, we start with the basic y equals log x, and then log of 3x, which means there is a horizontal shrink of a factor of 3. And if you look at this function, which is the basic log y equals log x, look at the color. This takes place at 1, 0. Now it shrinks by a factor of 3. It becomes 1/3 0. So first, this was located at 1, 0. And now we have this point located at 1/3 0. So we want to be absolutely clear as to what happens with the transformation. Since we have 3x minus 4, if we take the 3 out, because we have it here, times x minus 4/3, means it has been shifted to the right by 4/3. So shift right by 4/3. So you're looking at this blue one. This one shifts right by 4/3. And if it shifts right by 4/3, this 1/3 over here, you add 4/3 to it, becomes 5/3. So this point has coordinates 5/3, 0. 5/3, 0. The most important thing is to understand why 5/3. Now we're going to work on this negative sign. That means it's going to flip over with respect to the x-axis. It's going to reflect across the x-axis. So this thing will flip over with respect to the x-axis. When it does that, so that's the effect of negative sign. When it does that, the graph flips over, but the location of this x-intercept remains unchanged at 5/3, 0. So this still has the same location, 5/3, 0. Now the next thing is to look at this one, the one in purple. Now we are going to add +3. So we're going to shift this up by 3 units. So we're going to shift up by 3 units. So this purple one goes up by 3 units, becomes the black one. So what happens is that this point, which at the coordinates 5/3 0 has gone up to 5/3, add 3 to that. Whatever this number is added to the y coordinate. Since y coordinate is 0, becomes 5/3 comma 0. And then this is your vertical asymptote. To find the vertical asymptote, basically, if you set this equal to 0, x equals 4/3. So VA would be to set the argument of log equal to 0. So here's the graph. It's a little bit more detailed. That's the same graph. We went through the transformation. Here's the same graph. The vertical asymptote, set 3x minus 4 equal to 0, and it gives you x equals 4/3. And the original x-intercept of 1, 0 through all these transformations as a new location 5/3, comma 3. So from the graph, you can see the domain. Since the vertical asymptote is 4/3, the domain is 4/3 to infinity because it's this side. The range, according to the graph, makes no difference, all real numbers. And the end behavior, when x gets closer and closer to 4/3, it blows up to infinity. As it goes to positive infinity, x goes to negative infinity. It's going to go down. It can't be shown here, but it's going down here. So this is the domain, 4/3 to infinity. 4/3 is not included. Ranges are real numbers. And here's the end behavior. All right, we want to expand the logs. In other words, we want to use the formulas that we have seen. These are the properties. In this case, we can use the product rule. It's simply log x plus log y plus log z. Don't forget the same base, namely 7. It's important to pay attention to the base, everybody. The next one, we are going to use the quotient rule. ln of the top, ln 9 minus ln of the bottom minus ln x. For this one, we're going to use the power rule. We take the 10 down and make it a coefficient or a multiplier. Now, this one, we use a combination. We can do it in one shot or in 2 shots. So I can write this as log of the top minus log of the bottom, and I'm going to use the same base, whatever it is, it happened to be x. And now I can separate this one to log a squared plus log of b to the power of 4. And this becomes 2 log a, this becomes 4 log b, minus 7 log c, and all of them have the same base. Again, you can do it in 1 or 2 shots. If you want to separate this, I can write that also. So this piece, you write it as log a squared plus log b to the power of 4. Again, all of them You want to be careful with the choice of base. You always use the same base that is given to you. This is another format. These are the same formulas. Let's continue. All right, we want to expand each log again. And we start with the first one. We rewrite this to the power of 1/2. And so 1/2 sits in front. I can get rid of this and put it in front. And then it's 1/2 log of x cubed plus log of y to the power of 5. For this one, 3 sits in front. For this one, 5, and then times 1/2. So those are the answers. This one very straightforward. Ln of the top minus ln of the bottom. There's really not much to it. All right, now this one, we can write ln of the log of the top minus log of the bottom. All of them use the same base, namely 4. Although it can be done in one shot, but just in case, this one is x to the power of 1/2. This one is 10y to the power of 1/3. And so what we have here, let's just separate them. Log base 4 of x to the power of 1/2. Plus log base 4 of 10y to the power of 1/3, and you just repeat the last part. And so what happens that 1/2 sits in front, 1/3 sits in front, and minus 10 sits in front. And this one we can cut it into two pieces. This piece, everybody, it's log of 10 plus log of y, and the 1/3 sits in front. So this is what we end up with. Okay. That's the final answer. Very straightforward. I hope everybody is comfortable with that. I'm going to go back and put them back together. So in this case, it's log of 2x to the power of 4 times 3x to the power of 5. And it becomes log of 6x to the power of 9. In this case, it becomes ln of 6x to the power of 9 over x squared. So ln of 6x to the power of 7. In this case, we get rid of the 2, we put it here. In this case, we get rid of the 3, we put it here. And now we use the product rule, the reverse process. We multiply them together. In this case, we get rid of this and we make this square root. And we get rid of this, we make it to the power of 3. And I hope you see that I can combine these two into log of x z cubed minus a log of square root of y. And by the way, for this one, they may want you to multiply them through, okay? Not me, as far as I'm concerned, that's good enough. And so this is the final answer. All right, we want to solve. The fact is, if we have the same base, we must have the same exponent. They have the same exponent, we must have the same base. These two have the same base, so these two must be the same. So minus 4x minus 3 must be the same as minus x. And I can move this to this side. Becomes 4x or 3x equals minus 3. If I divide by 3, I get negative 1. For part B, we are going to change the 64 to 4 cubed and 16 to 4 squared, and everything has a base 4 now. As you can see on the left side, we have a 4 to the power of 3 plus 3x. This must be the same as 2. And so 3x equals negative 1. X is negative 1. Again, pretty straightforward. Two e to the power of 3x is 13, so divide by 2 first. And since the base on the left side is e, you take a natural log. So the left side becomes 3x. Now, if we divide both sides by 1 by 3, or you can say this side multiplied by 1/3, it means the same thing. Now, this is an exact answer, everybody. And with a bunch of decimals, this is an approximation. It can be done just the way it is, or by substitution. If you want to do the substitution, you let this one be, for example, y or z. You can't use the same variable x just for the sake of argument. If you were to say this is y, I hope you see that this is y squared. Okay, and the factoring is y minus 3y plus 2 equals 0. But just the way it is, you can factor it in this format. It's your choice whether you want to use a substitution or not. Now, the first one says e to the power of x is 3. The second one says it's negative 2. And I hope you know that this has no solutions, because exponentials, if you remember, the range is from 0 to infinity, so there is no solution here. And this one, you take a natural log of both sides. The left side becomes x. And again, ln 3 is the exact answer. You really have to distinguish between the two. Many times we want both of them, but you always start with the exact answer. We continue with the same concept, whether it's exponential or logarithmic format makes no difference. If they have the same base, they must have the same exponent. If they, in this case, if they have the same base, they must have the same argument, and vice versa. So this one, we go with the definition. So we say 9k is 3 squared. As you know, 3 squared is 9, therefore k becomes 1. Anytime you have a bunch of logs on one side and a bunch of numbers on the other, you put them into a single log, and then you use the definition. To put it to a single log, you multiply these two 4 times minus 5x, and it becomes log of negative 20x. And now you go with the definition. This has no base. That means the base is 10 because it's a common log. So 10 to the power of 2 is minus 20x. 10 to the power of 2 is minus 20x. As you know, 10 squared is 100. And if I divide by negative 20, I get negative 5. Now, before we move on, it's important to know that the basic domain of a log is positive values. So if I put minus 5 here, it becomes positive 25, and therefore it's okay. As you can see, in both cases, we have logs on both sides. And since this one has the same base, must have the same argument. Okay, 1 log on the left, 1 log on the right. So 5n minus 2 equals 8 minus 5n. We're going to move things around as follows. n equals 10, n becomes 1. The next question, both sides have logs and nothing else. If any side has a number, then you bring all the logs to one side and you keep the number to another side. Since both sides are just logs, put each one into a single log. The left side is fine. The right side, you can multiply 12 and x. And now because they have the same base, namely 10, they must have the same argument, namely x plus 12 must be equal to 12x. If I subtract the x from this side, becomes 11x, and divide by 11, x is 12 over 11. Again, the very first question, all of them are logs and nothing else. We don't move anything. We make the left side into a single log. The quotient rule, ln of x plus 4 over x. But the right side, we don't touch it. They have the same base, namely e. They must have the same argument, therefore. And so we multiply these two, we get x plus 4. This is a cross product. We multiply these two, we get x squared plus x. We can drop the x from both sides. If x squared is 4, x is either 2 or negative 2. When we check 2, that works here, that works here, that works here. When we check negative 2, works here, but doesn't work here, so negative 2 is out. So again, negative 2 is fine for the first one, but not the second one. You don't even have to check the third one. As long as it fails once, it's done. When we look at part B, we notice the right side is a number, the left side is not. We put the left side together using the product rule. So log of x times x minus 1 with the same base, namely 2. And now we go with the definition. X times x minus 1 is 2 to the power of 1. And so this is x squared minus x, and we move the 2 to the left for the sake of factoring. It's x minus 2 times x plus 1. X is either 2 or negative 1. If you go back to the original function, 2 works here, yes. 2 works here, yes. Negative 1 works here, no. You don't even have to check with this one. It doesn't work here, so negative 1 is out. Because the argument must be positive. The argument must be positive. We want to solve this. First and foremost, we're going to subtract 10 from 3, and it becomes negative 7. And this has no solution because the range for basic exponential function is 0 to infinity. So it can, 4 to the power of x can never be negative, can never be 0 either. To solve for part B, one easy way is notice that 1 is any number you want to the power of 0. Because this has base 7, Let's write this as 7 to the power of 0. So x minus 10 must be 0, and therefore x must be 10. Again, this is an easy way of handling that. When you look at a case like this, you notice there is no way that we can make the same base for both sides or the same exponent. So in this case, we have no choice but to take a log, and you take a common log or a natural log really makes no difference. The reason it doesn't, if this was, for example, if any of them were e, you would take a natural log. If any of them were 10, you would take a common log. Since we don't have any of them, it makes no difference. So let's go with one of those. So let's take the natural log of both sides. This one x becomes the coefficient. This one x minus 2 becomes a coefficient. What's important is to know ln4 is a number. It's not missing. I want to stick with ln4 because it's an exact answer. The same thing here. Since we are solving for x, let's distribute. Please understand, is x times some number. So since we are solving for x, we want to bring these two together. So I'm going to move this one to the left. And it becomes negative. I can factor the x out, and I can divide by the parentheses. Now, it is important to know if we had moved things differently here. That means if I had moved this to the right and this one to the left, this would become, take a look at this negative sign, this would become the following. So if you see this one, 2 ln 9 over ln 9 minus ln 4, it's the same answer. Meaning, you see this negative sign, if you take it down, becomes this. It's just how you move things around. Assuming log 2 is a, log 3 is b, log 5 is c, and we don't know the base. The base is something like b. How do we evaluate those? We have to factor. I'm assuming everybody's okay with the factoring. 50 is 2 times 5 squared, because it's 2 times 25, and 25 is 5 squared. I will show you on 300. And so this is log 2, this is 2 log 5, and all of them the same base. And now you replace this with a, you replace this with c, and you're done. If we want to move here, first understand this is 300 to the power of 1/5. So 1/5 becomes the coefficient. You have to factor this. And I, again, just reminding you, we are dealing with prime numbers 2, 3, 5, 7, 11, 13, 17, so on and so forth. So you want 300, you divide by 2, you get 150, divide by 2, 75. I can no longer divide by 2 because 75 is not divisible by it. I go to the next number, which is 3, gives me 25. I can no longer divide by 3. I divide by 5, gives me 5. 5 again gives me 1, and this makes it done. And this is the factored format, 2 squared times 3 times 5 squared. By now we can break this into pieces. So this is 2 log 2, this is plus log 3, this is 2 log 5. And now you replace them. And we get 1/5 of 2a plus b plus 2c, which is the final answer.